Okay, hello. Some of you have noticed on the internet that there's quite a few YouTube videos that I did for previous versions of the Special Relativity course, and I decided this works. People seem to enjoy it and get something out of it. So I'm doing it again this year, and there'll be lectures for support for preparation for the first year PHY 101 exam, and today I'm just going to do a run through of the problem that I set as an example in lecture 8, because I didn't ever show up to lecture 8 to actually deliver the material. So you've got the notes but you haven't had the lecture, so I thought I'll write that wrong before I get started with the revision lecture material. So the problem has to do with an electron and a positron colliding. Each of the electron and the positron has a mass of 0.51 MeV over c squared. And it tells you in the problem that they've got equal and opposite momenta and they're collided head on. So it's a colliding beam accelerator. And so they come together and they fuse to form a single particle. In this case it's a Z0 boson. And the Z0 boson has a mass mz of 90 GeV upon c squared. So that's about 180 times the mass of the incoming particles when they're at rest. And so the question is, what's the minimum energy that the electrons need to have in order to make the Z boson? So you might guess the answer to this. The guessed answer is that they each need to have 45 GeV of energy, and then when they collide together the energies add up and that produces enough energy, 90 GeV, to make a particle of mass 90 GeV upon c squared. That's the guess, and it turns out it's correct. However, it would be nice to verify that that guess is consistent with something we know for special relativity, which is that total energy and momentum are conserved as long as the observer who's measuring those quantities is in the same frame of reference before and after the collision that occurs. So let's just check that. So let's write down those numbers for this problem. So before the collision, you've got an electron, and let's say the electron's moving to the right, and it's got some energy E, and it's got some momentum P, right? And you've also got a positron, which is basically this particle of the same mass, and it's moving to the left, and it's got energy, well, let's call this energy E plus and this one energy E minus. Sorry, let's call this one energy E minus because it's an electron, this one energy E plus, and then this one has momentum P minus, and the positron has momentum P plus. And let's look at what happens after the collision. So after we have a single Z at rest, and it has momentum Pz equals 0 because it's not moving, and it has energy Ez equals the mass of the Z times c squared because it's at rest. Okay, so let's just see what energy and momentum conservation tells us. Well, the first thing it tells us is that P plus plus P minus, the sum of the momenta, must be 0. And that's because that's all the particles we have to start with, so their total momentum must be the same as the total momentum of the things we end up with, which in this case is a single Z0 at rest. So that's our first equation, right? Which means that P minus has to equal minus P plus, so the momenta, as we always say, are equal and opposite. Okay, so now let's see what consequences that has for the energies. We know from the energy momentum mass conservation equation, the energy momentum mass relation that we learned during class, that for a particle with energy E and momentum P and mass m, the square of the momentum equals the square of the energy equals the square of the momentum times c squared plus the square of mc squared, which sometimes people write as m squared c to the fourth. Now in this case, P minus and P plus only differ by a sign. So if you plug either P minus or P plus into this equation, P squared comes out the same, right? Which means that the left-hand term on the right of the equals sign is the same for both the electron and the positron, because you square it and get rid of the minus sign. But in addition, both the electron and the positron have the same mass. So that means that the right-hand term on the right-hand side of the equals sign is also the same for both the electron and the positron. And so the entire of the right-hand side is the same for the electron and the positron. And therefore, the left-hand side has to be the same for the electron and the positron. And so that means that our next equation is that E plus squared has to be equal to E minus squared. You can take the square root of both sides of this equation, and noting that energies are always positive, we must have that E plus equals E minus. They have the same energy. So we started with conservation of momentum. That leads us to the idea that the momenta of the two particles coming in are equal in magnitude and opposite in sign. Then we plug that into the energy momentum mass relation, and that leads us to the conclusion that the square of the energies have to be the same for the electron and the positron. And then finally we take the square root of that equation. Noting that energies are not negative, we deduce that E plus and E minus are the same thing. So if we've got both those things being the same, we might as well call them just both E. Right? Now we're in a position to do energy conservation. So the initial energy is E plus plus E minus, but that's just 2E. So that's the energy before the interaction. And the final energy is mzc squared. So that means that the energy of each of the electron and positron is mzc squared over 2, which equals 45 GeV. Okay? If the mass of the Z is 90 GeV. And that is exactly the same as the guess we initially made. The energy of each of the electron and positron has to be 45 GeV in order to make the Z0 at rest. Right, so part 2 of this problem, we change things slightly. And we go backwards a little bit. We say, okay, we've got a backwards experimental designer. He's an experiment designer, he's not very good though. And he proposes that we simplify this collider by making the target at rest in the lab. So instead of having a beam of positrons and a beam of electrons coming together in the centre of mass frame, the same frame as the lab frame, and the momenta are equal and opposite, so the centre of mass frame and the lab frame are the same frame. Instead, in the lab we'll have a block of material containing some electrons, nominally at rest, and we will fire at that block of material a beam of positrons, which will somehow create. So if the electrons are at rest in the lab, how much energies does the positron have to have in order to make a Z0? Now here you might make the guess that given that the answer was 45 GeV each when the electron and the positron had equal and opposite momenta, you might guess that if the electrons are stationary, then the positrons coming in would have to have twice the energy, 90 GeV, in order to make the Z0. Well, you'd be completely wrong. It doesn't work like that, because as we'll see, there's difficulties that arise from the fact that you are not anymore in the centre of mass frame when you're standing in the lab. And we'll see how that works next. So let's clean the board. I can find my board duster. So now, initially, we have an electron, and it's at rest in the lab, and we have a positron coming in, and it has energy, we'll call it E. We'll call it E primed. plus. So we are starting in what we would call the primed frame here. Okay? And it comes in and it hits the electron. Now the question is, how do you approach this problem? Well, what happens at the end of this? Well, the first thing that you might notice is that things are not going to be as simple in this frame as they were in the centre of mass frame, because what you make in the end is your Z0, just like you did before. Only because of momentum conservation, it can't be true that the Z0 is made at rest. It must be moving, it must have some momentum. So we could call this momentum, for example, PZ primed. And so, if you wanted to figure out what the momentum of the Z0 particle was finally, you'd have to do momentum conservation with the positron momentum calculated from its energy using the energy momentum mass relation, and you could then deduce the final state momentum of the Z particle. But in no way can you arrange for the emerging Z particle to have zero momentum. You can, of course, arrange for the Z0 to have zero momentum if the electron isn't initially at rest. If the electron's moving that way, then you could arrange for the Z0 to be produced at rest. But thinking about it, what you're doing then is you're going back to the centre of mass frame. Right? So in the lab frame, if you have a fixed target, if you have an electron at rest, you cannot have the final state being a Z0 at rest. And that makes the problem quite a little bit more complicated, nominally. However, there's a trick which enables you to do this problem quite easily. And the trick is simply to note that we've already done the problem in the centre of mass frame. So we know in the centre of mass frame, Cm, that if you have a 45 GeV electron positron coming in, and a 45 GeV electron moving with an equal and opposite momentum, equal in magnitude but opposite in sign, then you can make a 90 GeV Z0 at rest. We know that. We can make a 90 GeV Z0 at rest from two positron and electron moving with equal and opposite momentum towards each other. So all we actually have to do is to take this set of physics and Lorentz transform it to the frame where the electron is at rest. And if we can do that, we will have found the energy that the positron has in that frame, and we know that the Z0 is produced. If the Z0 is produced in the centre of mass frame, it will also be observed to be produced by an observer in the frame in which the electron is at rest. So if we can figure out the minimum energy that the electron and the positron need to have to make the Z0 in the centre of mass frame, then we can, by Lorentz transforming that quantity, we can discover that the energy that the positron has to have in the lab frame to make the Z0 in the lab frame. And okay, the Z0 won't be at rest, but it's the same physical production of the Z0. It doesn't matter what you frame in, it's still the threshold for the production of the Z0.